announcement. So this is how the assignments and the weekly homework is going to go. So every week, just like I've done here, I'll give you a notebook. It will have something to do with what we have taught that week. So since last week, it was all about Python and pandas. That's the homework that I've given. And then finally, these assignments, the way you can actually submit them is by using this link. So just do a share here and copy the link to the actual the actual notebook, and then take that link and then just submit it in your assignments right here. So just use virtually to paste the notebook's link, and this notebook will be a judgment of your level of participation. There will be a final assignment that is going to come at the end of week 5. So at the end of week 5, we will hand out a PDF document that will be a bunch of questions that will actually ask you to do many things at once. So it will ask you to do exploratory data analysis. It will ask you to do apply those models. Can everybody please mute yourselves? Can hear someone? Okay. So yeah, as I said, the final assignment that will be given on week 5 will have lots of questions. Those questions will be a final culmination of this whole thing. So you'll be doing exploratory data analysis, text screening, text processing, and then applying a machine learning model, and then actually showing the evaluation metrics and all that. And that assignment will be the final assignment and that is the assignment that you will be graded on. The weekly assignments are like homework. So you need to do these assignments because these assignments will actually build up your skills, because machine learning is not just about theory. You also need to know how to actually apply them in practice. So these assignments will help you with that. Submit the links to the notebooks on virtually. I can go in and check those notebooks, but your final assignment, the PDF document that we will be sharing at the end of week 5, that is a very important assignment that will actually be graded. It will have all the questions that combines these assignments. And then every week, just like now, I will be discussing the previous week's assignment so that you can compare your solution to what I've done, and then you'll understand how to actually do it better. Are there any questions regarding this?
Yeah, hi Ani, could you please show us again how to submit that again, and just using that link?
Okay. So yeah, here, like when you click share here, you will see some you will get a link automatically. So you can just say change, you can add the organizers here. Like you can just add, like virtually will anyway take care of it in such a way that your assignment will only be visible to us. But if you still want, you can just add me or organizers as people, and then you can just get the link. You can just you'll get this link, and just copy this link and paste it inside virtually, and then I can open the notebook and check your code.
Sorry, so just to confirm. So when you share, you need to make sure you set the right permission. So yeah, it's get link part. So anyone on the internet, that is correct. So if if you are using a school account or something, yeah, you need to change this to anyone with the link, and then you can just give us the viewer permission. That's enough.
Okay, thanks.
So
and also
don't forget,
one more, yeah.
Yeah.
Okay, so one more question. So we need to share only that the file notebook with only the answers, right? The final answers, not the analysis part.
We will inform it to you every week. Like this week, that's how I wanted you to do it, but next week can be different. Whatever it is, I will tell you how to exactly do it. If it's code, I will actually ask you to the code. If it's values, I will actually ask you for the values.
Okay, so for this week only the values, right?
Yeah, for this week it's just the values is fine. Yes.
Okay, thank you.
I mean, if you want, also submit the analysis notebook as well. I can take a look at that as well. If you have the analysis notebook separate, just submit that with the in the virtually as well. But make sure that this is not restricted. Otherwise, we can't open the notebook. So make sure that it's anyone with the link.
Okay. Thank you. Yeah, that's answer my questions.
Okay. Okay. So now that we're done with that, so let's get started. I'll just take about 15 minutes to go over the last week's assignment. So let's actually look at the first question. So create a list of integers starting from 1 to 100,000. So some of you might have used for loops. That's okay. You can use any technique you want. One very quick technique is called list comprehension. So it's called list comprehension. You can read about this, and this is actually a very useful technique. So list comprehension means you just define a list, and within the list itself you write a for loop. So this is how I would do it. I star star 2 means I square. So I'm saying I square for I in range. I asked from 1 to 100,000. So it's 1 comma 100,000 plus 1, because that's how range works. Range always gets the last but one number. So, oh, sorry. Yeah. Okay. Okay. I think this is the maximum zoom. So, okay. Yeah. I hope this is fine now. So, okay. So now, so Ho Young, yes, you can submit the full analysis and the final results both. I can check them. Okay. So if you see this is called list comprehension. So this means within the list, if you see the square brackets, I've actually defined the list, and then within the list, I've written a for loop. This is the same for loop that you write in 2 lines. I've just written in 1 line. So now let's actually run this. So if I run this, so if I do squared integers now, you see I got the I got those squared integers. So let me print it. Okay. So now this is what happened. So if you see, the squared integers automatically got created, like the whole list. So with this one line, this is how I would do the first question. So this is called list comprehension. And now moving on to the next one, create a function to print the maximum of 2 values. So you can do this with simple if-else statements. That is fine, but Python actually provides a function for you, and that's just called max. So let's actually see how that works. So max 10 comma minus 87. So it's just going to give you the maximum value. So that's it. It's how simple that is. So when I ask, if you have to define a function, all you need to do is, as you've learned before, how do you define a function? So you say def, and then you take max 2 numbers. So max 2 numbers, and then a comma b. Those are the inputs. Okay, I don't know why it's so slow. Okay. After this, just say return max a comma b. That's all. So essentially, you're just creating a wrapper over this already existing wrapper. So under max function, you're finally it has those if-else statements. It's much more optimized for dealing with larger numbers, but essentially that's what's going on inside. So just say max of a comma b, and that's all. It's a built-in Python function. You don't need to do any import or anything. It's not related to pandas or numpy or anything. So next, how do you do this? Okay, I hope there are no questions until here. So how many columns and rows are there in the test data set? So for this, all you needed to do was use the shape function. So let me, where is the, yeah. So for this, all you needed to do, let me type all the solutions below. So here, so if I read the file, okay. Now, what was the question? The question was number of rows and columns in the data set. The simple answer is just df.shape. Now df.shape, 418 is the number of rows, and then 11 is the number of columns. So that's how you actually do it. Okay, so now that's what I would just write here anyway. So that's that one. Now, what is the youngest and oldest age recorded on the ship in the train data set? So let's see how to do that. So df underscore train. Let me read that once more. So now, what's the question? Youngest and oldest age recorded on the ship. So first we need to fetch the age. So how do we fetch the age? If you remember from pandas, you just select that column as it is. So you just say the df underscore train is the object that holds this data, and then all I'm is the data is the actual pandas data frame, and all I'm saying is get me the age. Now what is the maximum? Just do max. Now what is the minimum? Just do the min. That's all, it's finished. So that's how you do this this one. So 80 and then 0.42. 0.42 seems odd, but that's okay. We'll learn about data cleaning later. But for now, that's how you actually do. I just use the max and min functions, and then I did pandas data frame to actually select that particular column. You're right. You're right. Sorry. Okay. Okay. Yeah. Sorry. That is right. So 80 is the oldest and 0.42 youngest. So that's the oldest and youngest age recorded. Now, what are the proportions of the female passengers? This was a bit confusing. So proportions might sound like percentage, but that's why I specifically mentioned save the integer number. So I actually needed the number of, all I needed was the number of male and female passengers. So the standard way to do this is just use an if statement and give over that column. And if this is a male, count, increase the male variable. If this is a female, increase the female variable. That's the standard way. Yeah, just to answer Zach's question, you can do that. That's pandas. So sorry. So this is pandas function. You can do this as well. So there are multiple ways to do it. It doesn't matter how you do it. The fact is you just got the answer. So you can use multiple ways to get the max value. So how do you actually count the number of female and male passengers? So this is how I would do it. You just, so first of all, which column has the female and male passengers? Let's actually check the data. Like where are the female and male passengers? Okay, this column. This column actually says it's a male or female. So first, let me select that column. So now I've selected my column. How do I count? You don't need to use for loops. You don't need to use anything. Pandas has very optimized built-in functions, and it's called value counts. So that's all. I've got my answer instantly. So you don't need for loops or anything because pandas has very optimized built-in functions. So this is what I expected you to actually research about. So pandas, once you explore pandas, it actually has lots and lots of built-in functions that are actually very useful. So dot value counts actually gave me the answer straight away. What if I wanted the percentage? I could just divide it by the shape. That's it. So that's how you can get it. So value counts is such a function to get the proportion of these two categories. So, okay, let me just write it down. 577,314. Is that right? Oh, it's a reverse. Okay. Okay. So you don't need, so proportions. So as I said, just save the integer number. You don't need anything else. You don't need to normalize or anything. Just save the number as it is. Now let's move on to the next question. What is the average ticket price per passenger ticket class? Now, where is the passenger ticket class? Let's check the data again. P class. Okay, this is that's why I specifically mentioned P class. So basically, P class is the passenger ticket class. Now, what I want to actually do is the average price per ticket class. So, okay, let's actually check how many there are. So we just did value counts. Let's actually do value counts again for this. So P class dot value counts. Now there are 419 tickets for the third class passengers, 216 tickets for the first class passengers, and 184 tickets for the class 2 passengers. Now I want the ticket price per passenger class. So for these 491, what is the average ticket price? So you sum up all the prices of all the class 3 ones and then divide them by total 491. How do you do this? You can use a for loop. You can check for the class 3, add it in a variable, and then divide it by 491. Another better way is something called group by. And this is actually a very useful function that you will keep using again and again in the future. But basically, okay, this is how you do. So group by means it's going to group all these classes. So you have class 3, class 1, class 2. So group by is actually going to group. It's okay. If you're familiar with SQL, it's like aggregations. It's just going to group all these classes, all these whatever you want into one group and then perform aggregations. So let's actually do group by. So group by what? So by, I'm going to group by P class because that's what I want to group by. And then dot, I'm just going to say mean because I want the average. So now passenger class 1 has fare $84. Passenger class 2 has average fare $20. Passenger class 3 has average fare $13. That's how you get the passenger class average price per ticket class. So the reason that I am not giving, I want you to actually do the research is because that is how it is everywhere for data scientists. You are given not even half the problem, quarter of the problem. You don't even know what to do. You always have to do research. And this is how you actually can get into that mood of doing research and finding out. So you always have to read the documentation and go over all those stuff and try to find out the different functions, because we can't learn everything at once. But through research, we actually now you actually have been introduced to two most common functions. This is actually very useful. Now you will remember group by is used for grouping by certain categories in this way, and value count is used in this way. You'll remember this and you'll start using it in the future. This is all research is all about. So just that's why I'm asking you to do these things. So this is not the only way to do it. There are multiple different ways. It's just that I'm trying to get you used to pandas because pandas is actually a very well developed library, and I want you to use that more. Okay, this is a this is a bit complicated. This was very tricky. Okay, this is the last question. After this, I'll start the class. So explore the names feature and find out how many titles are present. A title stands for Mr., Miss, Doctor. So for this, there's no straightforward answer. So first, you would have to actually look at the data properly. So I think it's called names. Okay, name. Okay, so if you look at the name, let's actually print it. Okay, so if you look at the names, so these are the titles. So Miss, Mrs. There's always a dot and then Mr. and then, so you need to just take a glance over this. Luckily, there is a pattern that I can notice right here. It's always some set of words and then followed by a dot. It's always like that. It's always, so that's actually lucky for us right now. It's always there is some dot and then there's a word followed by the dot. So let's try regular expressions. Not sure. So basically, if you are not familiar with regular expressions, try to understand that. I would say this is a very good place to understand regular expressions. So W3 schools. So Python regex in W3 schools. This is a very useful website to understand regular expressions. So this website it will teach you about all these how to actually use regular expressions. Basically, it's a way of capturing some patterns. So this is kind of a pattern that we need to extract from the string. So basically, let's actually take this sentence. So for that, you would need to import the library. So RE is the library that you use to actually create regular expressions and then capture those patterns. So this is the string. So our test string. Okay. Now let's actually try to capture Mr. from that. So I'm going to say re dot find all this means so re dot find all means basically I'm going to enter the pattern and then I'm going to enter the string. It's going to, according to the pattern, it's going to fetch me whatever I want, whatever have matched the pattern. So let's enter the string first. Or test string. So okay, the pattern is just a regular pattern. What is the pattern that you observe? There are some set of words, then there's a full stop, and then there are again set of words. So the title is in between. So this is how I would do it. Capture any capital letters or any of the small letters. This is one group, followed by a dot. Let's actually see what happens. I think one or more. Okay. Now you see that I actually captured Mr. How did I capture Mr.? Regular expression rules tell me that this means A to Z means all the capital letters. If you see this, A to Z returns a match for any character alphabetically between A to Z, lowercase or uppercase. So uppercase means match any character alphabetically from A to Z. Lowercase means lowercase, uppercase means uppercase. That's what I did here. So basically I did A to Z or A to Z. That is one group. Plus means one or more. So if you remove plus, it means it's only going to capture one single letter. That means I'm saying capture only one letter. If I add plus, it means capture one or more. So that's what it says here. So plus means returns a match for any sorry, it's here. So plus means one or more occurrences. That's what I did here. And the lastly, I put a dot. So dot in regular expressions, dot means any character. But if I put backslash dot, it actually means this one. It actually means this character. So this is a bit confusing. I'll explain it again. In regex, just the dot means any character. So let me show you. If I just say dot, it's going to give me the whole thing because that's what dot means in regular expressions. But if I append it with backslash, I'm actually asking it to capture this dot over here, this full stop. That's the difference. So this is how I would capture. I would do this, and then all I would do is just capture these things and then count them in a dictionary. That's all I would do. There are various different patterns. Basically, you can stick to any one. How do you actually answer this question is finally you would get a dictionary and then you would say Mr. some number here, maybe 40 or something, then MRS and then something else. So that's the answer that you would get finally. So you would just use a for loop to count it. Okay, I think we are at 20 minutes. So that's for the assignment 1. Are there any questions? Yeah, when you use regular expressions, you might need to, you might still need to use a loop because you need to go through every one. But if you remember in pandas, I think I already introduced the apply function. So where is that? Yeah, this apply function. So instead of going through a loop, you can actually use this apply function and use that regular expression inside this here. So this is how we would do it. So you can do this. So you can say def train its name dot apply lambda x. Now I'm defining a function using lambda such that re dot find all and then just put this here inside. Now put x. X is the actual string. So put x over there. So you see, I got everything. That's how you use lambda functions instead of a for loop. This is much, much faster, and I would urge you all to use this. So that's how you do this last question. Okay, I think all the questions are done. Okay, I will leave those organizational questions to the organizers. So okay, now that you don't have any other questions, let's actually jump on to the week 2 part. So okay, I'll use my pen this time. Okay. Yeah, so finally, welcome to week 2. These are all the things that we will actually be covering. So what is so you let me, I can zoom in more if it's not clear. Maybe I'll just put it in this mode. Okay, so right. So let's actually start. We will start with these topics. What is machine learning? Let's try to get a refresher on all those concepts that we have actually learned last week. And then what is supervised and unsupervised learning? What's classification, regression? We'll actually go through a small exercise. Volunteers are appreciated. Otherwise, I'll just ask open-ended questions. What's linear? We'll start with the simplest algorithm. What's linear regression? Then move on to logistic regression, and then we'll start actually seeing how to actually apply them on Python. So the reason I asked in the group yesterday how familiar you are with probability is because there are certain terms that I'll be speaking and I will explain them. But otherwise, all the machine learning algorithms always involve some level of math. I won't go too deep, but I will cover what is necessary. So let's move on. So this is a quick refresher on all the machine learning topics until now. So you can submit the assignment 1 after this class. Don't worry, just pay attention to whatever I'm teaching. Forget the assignment 1 for now. Please focus on whatever I'm teaching now. So let's look at the first one, data sets. So data set is nothing but the data that you processed.
We are still seeing the collab screen.
Oh, sorry. I shared the, let me share the presentation. Okay, this is the presentation. Okay, so.
Thank you.
Okay, now I hope you can see the presentation. So as I said, let me start at the beginning then. So this is what we will be covering. We'll start understanding what is machine learning, and then we'll move on to supervised, unsupervised, classification, regression, and then we'll start with the simplest topics. We'll start with what is linear regression, logistic regression, and then we'll move on to some hands-on practice. Let me move on to the next one. Going way ahead. Okay. So just a quick refresher on all these concepts. So a data set is nothing but the pandas data frames that you've seen. It's just a table, or it's not just a table. It can be anything. It's just any data, audio files, video files, images. It can be anything that you process, transform, and use to train your machine learning models. What are features? So features are nothing but the individual columns, or it's just the features that how do you describe the data? That those are the features. Like the Yoda example, how do you describe Yoda? With the eyes, with the ears, and with the green color, and with the shirt and all that. So those are the features. Now, what is supervised and unsupervised? I will go into more detail in this, but essentially supervised is where you have some answers, and unsupervised is where you do not have any answers attached with each row. So that's essentially what is unsupervised and supervised. Now, there is one more class of problems, which is called classification, where you classify in a limited set of categories. Let's say I have a description of some product on Amazon. I'm going to predict in which category it belongs. Is it an electronic product? Is it a clothing item? Is it a cooking utensil? Or what is it? It's a limited set of classes. So that's classification. Regression is something like stock market prediction or weather forecasting. You can have, okay, the stock of some company can be $100.2, $199.654. Like it can be anything. That's regression. There's no limited set of classes that you can bucket the things into. That's regression. Machine learning is just a set of algorithms, and it's a framework where the algorithms learn by looking at the data and trying to understand the patterns inside the data. What's training and testing? So today we will actually learn how to split the data into train and test in the notebook. Otherwise, training is just basically taking the data set and then splitting the data set into two parts. One part is basically used to train the model, and the second part is used to test the model. The reason we do this is because how does the machine tackle unseen data? You have to simulate that before. So that's why you first train the model, train the algorithm on one set of data points, and then you test the model on unseen data points, because that is how you actually judge the performance of a model. If the model has seen everything, then it can predict everything. But if it needs to perform well on unseen data points, then that is how we do it. And then, okay, these are the new terms, decision boundary. So let's take the example of classification. Let's say there are few data points, and those data points are labeled as positive, and there are few set of data points, those data points are labeled as negative. How do you separate them? How do you separate these two things? So decision boundary is nothing but it's sort of a line or a hyperplane or some kind of an equation that actually splits the entire data set into two distinct categories. If it is a binary, if let's say it's positive and negative, that's all you're doing, then a decision boundary is nothing but it's a boundary between the two classes. That's what this decision boundary is all about. Next, hypothesis. This is not the hypothesis testing from statistics. Hypothesis is nothing but the model that you would like to determine. This term might come up somewhere in some machine learning blogs or some textbooks. Most likely textbooks will use this term, but essentially hypothesis means your model, your linear regression model along with your parameters. That's your hypothesis. Weights and parameters. It's this, okay, weights and okay. If you understood features are nothing but individual columns. Now, weights and parameters are the values attached to those features. So the machine learning okay, ultimately today you will see that machine learning is nothing but a big equation that actually is a product of a column and a value. So it's something like 0.5 x1 plus 5.6 x2 plus so on. That's all the machine learning algorithm is all about. Weights are nothing but the the importance that you give to these features. If it's let's say it's a plant classification task or something, I want to identify the species of the plant. The weights are nothing but how much focus I want to give on a particular column. Let's say I want to focus on the I want to give more importance to the color. The color is such a good predictor, one good predictor for the species of the plant. So I will give more weight to the color. Maybe they measured some kind of like they did, I think it's called chromatography or something. They measured some kind of number and then they put some value to that the color. Now I will give more importance to color because I feel that feature is it's helping me determine the plant species easily. That's what weight is all about. And the last thing is ground truth. So basically, ground truth is nothing but the actual label, the actual values that you provide along with the data set. Where in our case, in the Titanic data set, we have this survived column. So if you look at the survived column or any column, basically it's just any column that finally the column that you actually want to predict. In Titanic, if you have gone through the Kaggle website already, you can see that it's Titanic survival prediction rate. So survival is given by 0 and 1. So 0 means they didn't survive, 1 means they actually survived the accident. So ground truth is nothing but I'm actually telling you that this data point has actually survived. This person has not survived. That's the ground truth. When you actually make a prediction, you compare your results to the ground truth. So are there any questions here? Because these are the point names that I'll be throwing around continuously. Okay. Now let me move on to the next one. So supervised learning. So this is what I mean by supervised learning. So I have the labels or the answers and I have the data set. So the data set actually consists of it's a data point and it's attached with a label. I'm going to feed it to the machine learning algorithm. The algorithm actually tries to mimic the data set and tries to understand the features. And then when a new unseen data point comes in, so let me take this pointer. Okay, so when a new unseen data point comes in, then finally you input it to the this same trained machine learning model, and then finally it makes its predictions. These predictions are based on these labels and then these data points. So it needs both of them. That is super. So you are supervising the algorithm. You are actually giving it the answers. That is what. So basically, this is something that's always going to be there. That is how supervised learning works. Now let's look at unsupervised. So there is no ground truth. So there is actually no, there are no labels. The data set is given as it is. One of the purposes of unsupervised learning techniques is to actually understand the structure of the data to group them into buckets. That's one of the purposes. And the class of algorithms are called clustering. So if you see here, so clustering is one common technique to actually get that. So basically, the key thing to understand is supervised learning, there is ground truth. Unsupervised learning, there is no ground truth. That's it. The class of algorithms that fall in this is called, one class of algorithms is clustering, because finally you understand the structure in the data. Let's say you want to group people. Like you want to group a set of people based on maybe some kind of criteria. Their scores, I mean, not scores, but basically you're trying to figure out what you don't know. That's unsupervised learning. There is something in the data, there is some structure in the data, but you don't know what that structure is, and you're trying to determine that structure. That's unsupervised learning. Are there any questions? Okay, so moving on to the next one. Now, classification versus regression. Let's actually go through this exercise. You all tell me which one is it. Is it C or R? Is it classification or regression? So let's look at the first problem. Predicting the sentiment of a given Amazon review. Output ground truth is 1 or 0. Is it classification or regression? Okay, that's right. You all got it already. I'll write that down here. So it is, okay, why? Okay, it is classification. Now let's look at the next one, weather forecasting. Output ground truth, the temperature in Celsius or Fahrenheit. Is this classification or regression? What are the answers? Okay, that is regression. Why is it regression? Just in one sentence. Yeah, real numbers, exactly. So limited set of categories or real numbers, continuous variables. That's much more better answer. Yes, continuous variables, no absolute answer. That is right. So basically, like you can have 38.67564 degrees Celsius or something. Like it's just you don't have any particular value. Stock market price prediction. The next day stock. I already told this. So obviously this is regression. Okay, this is very confusing. I don't know how many of you are going to get it right. Next word prediction in email. Is this classification or regression? Think about it very well. Next word prediction in an email. So whenever you type an email, you get the next word. Okay, half of you are saying classification, half of you are saying regression. So, okay, just think about it. How many words are there in the dictionary? Is it limited or unlimited? Too many, but still, is that too many unlimited or limited? The too many is still limited. The too many is still limited. A lot, but still limited. It can, so, okay, there might be a billion words or a trillion words or a zillion words. It still has a number. So that's why it's classification. So you might argue with me. You can search it up online, bring it up with me. That's okay. But there are always like a set of, okay, you take a dictionary, you have a set of words. So that's why it's, I'm going to say classification today. If you want to argue with me, feel free. I'm going to say it's classification. Now, can one of you come up with a new example for classification and one of you come up with a new example for regression? That's why I left the last one blank. Spam detection. Okay, that's a good one. Yes, spam detection is a good one. What about regression?
Predicting the cost of a house.
Yeah, exactly. Yes, those are correct. So yes, spam detection. That I'll write it here. Yes. So yeah, house pricing is that one. So basically, yeah, spam. Okay, my handwriting is not looking well here. Spam detection is classification, and then house price is one example. This is for regression. So I hope you all understand the difference between classification and regression now with this small exercise. Okay, so now let's move on to the next one. Now we are actually going to start with what is linear regression. This is the first algorithm, and this is actually coming from linear algebra. This is not something AI or so, not something very new. This has been there for, okay, this has been there as long as mathematics has been there. This algorithm is that old. As long as math has been there, this linear regression has been there. So let's actually go over this. What is linear regression? So basically, I think it's better to start with this one first, then I'll get back to the equation. So let's actually plot something. So I hope you are all familiar with graphs already. So let's say we have one variable x, we have one variable y. So this x is called the independent variable and y is called the dependent variable. So x is nothing but your input. Your you just gave the example of house prices. In case of house prices, the input can be the number of bedrooms, the size of the house, area, square feet, the number of, if there's a basement or not, those are the inputs. Output is nothing but the price. So let's actually check that. Let's actually assume that for now, x is only the, okay, let's just, for simplicity, let's just say it's number of bedrooms. So okay, so for now, let's assume x is the number of bedrooms and y is the price, the final price. My handwriting is bad, but yeah, try to follow that. So let's just plot some points here. So for x number of bedrooms, I'm going to get there's one point that's going to be over here. Then there's another point that's going to be over here. Then as the number of bedrooms increases, maybe the price increases. For certain number of bedrooms, this is the price. Then there's another price point here. Then there's another price point here. So each one corresponds to one. So if I draw one, so this point number x has a y value here. This point number x has a y value here. So like that, I will actually get so many points on this graph. So they keep, so basically they are a bit scattered in this way. So I can have points here, I can have points scattered over there, I can have points. Do you see that there is a pattern in this? As the number of bedrooms keep increasing, the house of the price also keeps increasing. I mean, obviously you can't, it's not realistic. I mean, maybe there are 10 bedroom houses, but essentially you can see an underlying pattern in this. Linear regression is essentially creating a best fit line to model these points. So linear regression, from this word linear, this means it's actually going to create a linear model. It's going to create a straight line that tries to best fit. It's a best fit curve problem. So it's going to best fit these points. How does it do that? So this is the best fit line. That's what I can see here. So if I draw a straight line here, so this is the best fit line. So now my model, the machine learning model, is going to take in these data points and it's going to give me as output this equation of the line. So you're not actually going to see the equation, you will see the coefficients. Those coefficients are nothing but those are the coefficients. Those coefficients are the weight parameters. The weights are the ones that make up this equation. So the simplest equation of a line, this is the simplest equation of a line. Y equals mx. If you're familiar with high school math, y equals mx plus c. This is the simplest equation of a line. So y equals mx plus c. So these are the weights. So this m and this c, these two are nothing but the weights. I'm calling it weights. Okay. So basically, linear regression, the problem is to create this best fit line. How do we create that? There are many techniques. So you must have learned some techniques, least square methods or something. There are so many techniques to actually figure out this line, the equation of this line. We will see how to do that. We will actually explore them mathematically, and then finally, when you actually do it in Python, the algorithm will take care of this for you. This is just for your understanding. So how does it do it? So this best fit line, the way it works is, it throws a random line first somewhere. This is the perfect line, but it actually initially, the way it starts is, let's say this is, I'll choose another color. Let me just, to make it more clear, I'll just Okay. Let me just do this. So basically, let's say this is the first random line that it threw. Like it doesn't know where the line is. It just took in the data and it just threw some random line. Now what it's going to do is it's going to check the distance from all these points. This is the first point. It's going to check the distance from this point to the line, this point to the line, this point to the line. It's going to check the distance from all these points to all the lines. It's going to check everything. So it's going to check the distance from that point to this line, that point, or it's going to check all these distances. And then what it's going to do is it's going to try to minimize that distance. So you see that this is sort of like a thread. It is like a thread game. Those lines have to become as short as possible. So now what it's going to do is it's going to take these distances, it's going to square them, and then try to minimize those. It's going to try to minimize the sum of the squares of all these distances. That is known as least square method. So it's called ordinary least square method. Now what's going to happen is it knows that the distance here is too high, so it needs to reduce. So let's say this is the next line. It's going to move slightly in this way. And now again, it's going to check distance from all the lines. It's going to check the distance from every line. And then again, it's going to know something. And then finally, it's going to settle at that blue line, which is the perfect best fit line. It might not predict everything correctly, but that is the best fit line that it can get for the data given. This is how linear regression works. Does anyone have any question? This is a geometrical way of understanding linear regression. To move on to the mathematics, this is how it works. So the y equal to mx plus c was the most basic equation that I've given. But essentially, sorry. Okay, ignore that. I don't know how to erase them. Just a minute. Okay, so basically, this is what happens. So the y equal to, instead of y equal to mx plus c, since we in case of house pricing, since we don't just have the number of bedrooms, we have so many other features. We have the square feet of the house. We have the, if it's a basement, if there's a basement or not, if there's a backyard or not, there's so many features. So all those features are nothing but these individual x values. So x1 can be number of bedrooms. X2 can be the average square feet of the house. X3 can be whether there's a basement or not. Beta is nothing but the coefficients, the weights. So the m and the c values that you've seen, those are the weights. So ultimately, every machine learning algorithm out there, it tries to learn the optimal set of weights to get the perfect value. To get the perfect y value, you need to get these optimal set of weights. How do you get those weights? There are multiple different techniques. One of the techniques was least squares regression. Ordinary least squares. Another technique is called gradient descent, which is what I'll be discussing today. And there are more techniques, but all you need to know is this is how linear regression works from a mathematical perspective. Are there any questions here?
Yeah, hi Ani, I have one question. So for this least square methods, as you mentioned, we need to find the best fit line. So is there any limitation for how many round we need to go for that? For example, at first it is showing that a random line, then we want to minimize that. So is there any line?
Okay. I understood your question. So basically, wait, that went away. Okay, so this was the point. So this was the best fit line. So in reality, there are linear algebra techniques. So the way that you can solve it is it's a minimization problem. So if you've done calculus before or simple linear algebra, basically the way that this error function is defined, this error function over here. So this the distance between the sum. So the distance between the line. So what we try to minimize is the difference between the difference between our predicted y value, the model's predicted y value, and then the actual ground truth. That is what it's comparing here. So basically, the way you can minimize that is just by taking the derivative of that equation and setting it to 0. So there is a closed form solution. So that is the most efficient way that is one of the most efficient ways to solve this. The closed form solution is nothing but you have the error function, you have the least squares error function, you take the derivative, set it to 0. This is the most common technique in minimization problems. The reason we do that is because the maximum or minimum exists whenever the slope of a line is 0. So I might be getting too mathematical here, but essentially, let me explain it another way. So let's say this is not related to linear regression, but I'm just explaining the concept of minimization. Let's say you have some curve over here. When you take this tangent over here, this is called a tangent. So whenever you take these lines over here, what happens is the derivative at this point, at this exact point, the derivative at this point is 0. So this means you have either reached a minimum or you have reached a maximum. So to solve this linear regression problem, you just take the derivative, set it to 0 and get the weights. It's done in one step. There is no iteration involved, but this is actually computationally expensive. Imagine that you have a billion rows and you're trying to take the inverse matrix of that. That's actually such a huge computation. So that's why iterative methods or methods like gradient descent are applied sometimes, so that as soon as one data point is introduced, gradient descent takes a step in that direction. So I will introduce that. I mean, I'm going much ahead, but essentially for your question, the answer is it's just one step. You just take the derivative, set it to 0 and get the weights. That's the closed form solution for this particular method.
Thanks.
Okay. Yeah. So Hussein, as you said, you have to take the derivative. You have to take the second order derivative and find it's the same thing. That is it's just math. That is what is used over here. So yeah, how to find the best beta? So beta is nothing but those weights. How to find the best one? Just by using matrix inversion, just as I said, or ordinary least squares method. It's the same thing. Gradient descent. So I won't be discussing too much of this, but I would suggest that you at least try to understand this. This is actually very important, this concept. So I'm just star marking it here. So maximum likelihood estimation is a key concept for understanding everything. So it's not a formula, it's not an algorithm, it's just a probabilistic framework. So it's a framework that so many machine learning algorithms use. Essentially, it is a probabilistic framework that tries to maximize the likelihood of a given function. That's what it does. When you actually read about this, you will understand that doing maximum likelihood ultimately will give you ordinary least squares result. So maximum likelihood is nothing but you have a likelihood function, you have a probability function that gives you the probability that this data came from this distribution. Maximum likelihood tells you to find how it's an optimization problem. It tells you to find out the maximum. It tells you to maximize this probability, this PDF, this function. How do you do that? Again, there are certain. You take the equation, you take the derivatives, you take it to 0, you do all that stuff, and finally you end up with the same thing. When you actually do the derivation, you will see that you end up with the same thing. So I would suggest please go and read maximum likelihood estimation. I can bet that people will ask you the same question in the interview. What is maximum likelihood estimation? So please make sure to read that. Today we'll actually focus on gradient descent, and the reason I'm focusing on gradient descent is because in the future in neural networks also you will see gradient descent keep coming up again and again. That's why I'm focusing on gradient descent for today. Okay. Moving on to the next one. So there are some terms that you have to understand first. What's a cost function? So if you remember the graph before, essentially gradient descent, okay, forget gradient descent, focus on the word cost function. So cost function is nothing but it's the what are you trying to do finally? Your machine learning algorithm is taking the data, is looking at, it's a supervised algorithm. So it's looking at, let's say you predicted your model predicted the house price is $500,000. Turns out the house price is not 500,000, it's 600,000. What is going to happen here is Y is actually the ground truth. So Y is actually 600K. And your predicted house price is 500K. So it's going to take these two, subtract them, square them, and then sum them up. Like that, it's going to take all the predictions. Another data point. Let's say you predicted, okay, we're in Toronto, so let's count in millions. So I'm going to say my house price, my model predicted 1.1 million. And then, sorry, the ground truth is 1.1 million. And my model predicted 900K. So I'm going to take the difference, I'm going to square it, and then I'm going to add it to the next one. So like that, it's going to take the sum of these things and then average them. So this is going to give me the overall error of my model. This is a way of judging the error. This is how linear regression judges the error of the model. It just takes the difference between your value and the final value and then squares it up. Now, why should I square it up? The reason is to avoid negative values. That's why you square these things. So, okay. Basically, what happens here is, now this cost for now the gradient descent algorithm, what it does is it basically takes this cost function, calculates the actual error, and then it adjusts the weights based on these errors. How does it adjust the weights is what I can show you in this graph. So this equation is a convex optimization problem. Because of the quadratic nature of this problem, it is called a convex optimization problem. I'm not an expert on optimization subject, so if someone else is an expert, I won't go too much into depth. But essentially, this is known as a convex curve, and a convex optimization problem means I'm trying to find the minimum. I'm trying to find this part. So I am trying to find the point where the cost is minimum, because if you see here, I want my model to be as close as possible. So if my model predicted 599K, I'm so close to the actual value. So my cost is very less. If I predicted 799. So if I predicted 799K, I'm much far ahead than what I expected. So basically what I'm trying to do is, if you plot this against theta is nothing but the parameters. Theta is nothing but theta is nothing but these values. So beta 0, beta 1, beta 2, these are all the values. So that's what I'm saying. So this theta is nothing but the parameters. As I keep changing the parameters, if I keep plotting J, this is the graph that you will get. Now what I'm trying to do is I'm trying to find the minimum point. The way gradient descent works is, initially the weights are assigned randomly. So let's say somewhere the weights are assigned, it starts here. So the weights, let's say this is where the weights are. So this is a 2D graph. In reality, there are so many weights that it's a multi-dimensional graph. But right now, assume that this is a 2D graph, and then for some random weights, the cost function is here. Now what it's going to do is, it's going to take a direction in the it's going to take a direction in such a way so as to decrease J. So it's going to take a direction in the step to reduce the gradient. So what it's going to do is, I'm going to take the derivative. Derivative is nothing but the change in Y. So derivative is nothing but this is the derivative. So I'm going to take dou J of theta. So I'm going to take the derivative of dou J with respect to the parameters. This is exactly what I'm going to do. After taking the derivative, I'm going to take the beta and I'm going to subtract the beta values from this. This is gradient descent. So to write it more properly, this is what happens. So beta I is beta I minus alpha times dou J of theta by dou theta. So what happens here is basically, what happens here basically is beta is nothing but the parameters. What gradient descent does is it tries to find out the derivative. The reason it tries to find out the derivative is derivative gives me the direction. So if I take the derivative here, I'm going to get this arrow mark. So I know that going in this direction will actually reduce the J of theta. How do I know that? I know that because of the derivative. Once I take the derivative, I will this alpha parameter is nothing but a learning parameter. Just assume that it's a constant for now, just ignore it for now. But essentially, I take the derivative, I'm going to subtract it from the existing random beta value, and the beta value is going to move here. Now, let's say I came here. Again, I'm going to repeat it. Again, take the derivative, again subtract it. I'm going to move down. I'll come here. Take the derivative again, subtract it and come here. I keep doing that until I come to this point. Now, what will happen here? Can anybody tell me what will happen at this point if I take the derivative? You can just answer in the chat. Exactly, it is 0. It is 0 because that is a tangent. There is no slope. Like the normal answer is there is no slope. So the derivative is 0. So what happens here is once the derivative is 0, this whole term goes away. So beta is just beta. It doesn't move anymore. So now you can stop here. I have reached the optimal point where I want to come for J, and then my model is trained. This is gradient descent. This will be introduced again during discussing neural networks, but essentially this is the convex optimization problem of how a gradient, I mean, this is gradient descent. This is how it works. In reality, I couldn't show the 3D point, but for 3 dimensions, it might look like this. I'll try to draw it, but it's not. So let's say there are 3. Let's say there are 3 parameters: theta1, theta2, and theta3. Let's say it looks like this. I'll try to draw my best. So this is the 3D diagram. Now it starts somewhere here, and it keeps moving in the direction until it reaches the optimal point. So for 4 dimensions, 5 dimensions, we can't even imagine them, but essentially that's how gradient descent works. So are there any questions? This is how linear regression works finally. So yeah, now I'll tell you what is alpha. So alpha is just a learning parameter. You set this to some values. Let's say you set it as 0.01. It doesn't work out, try another alpha, try another alpha. So this learning rate determines how far I have to jump. So if I set alpha as 100, what happens here is this point might jump from here to directly here. You don't want that sometimes, because let's say I'm actually here. If I set alpha as 100, I might actually jump directly to this point. I missed my optimum point. I actually missed it because of alpha. And then I finally come here, and then again I jump here. Again, I keep jumping here. It just takes too long to settle down. If I set alpha too small, what happens is it starts moving like this. It comes here, then it moves here, then it moves here, it moves here. It just takes forever to come to this optimal point. So alpha determines this jump length. I mean, to put it from a high level perspective, alpha determines this the length of how far I have to jump into this curve. Okay. Yeah. So Jin Yang. So instead of why we prefer this way is because okay, the optimal way, if I remember the equation correctly, I think the optimal way is this. So the direct answer is actually beta equals A x transpose x. Okay, it's something, don't write this, but it's something like that. Basically, you can finally get the answer. You can finally get the final answer just by multiplying them, but you need to do inverse matrix transform in one case. To take a billion row matrix, 1 billion by 1 billion matrix, and do the inverse, you won't have enough memory to do that. That's why we take this stepwise approach. You can try it actually. You can like define a random matrix with a billion rows and billion columns and try to do the inverse. It will take a lot of time. Stepwise algorithms are computationally cheap, but the most optimal way is to do it using those the direct derivative method that is said. Okay, I hope linear regression is clear now. So one thing to remember is you won't be coding any of these algorithms from scratch. You will be using the libraries. The reason you need to know this stuff is because, let's say tomorrow, your manager comes and asks you, your model gave me this prediction. Can you explain why? Why did it give this prediction? Let's take the house pricing example. Your manager comes and asks you, you're working in a real estate firm. You take all that data set and you just use your model. You predict it. You finally predict that this house is going to be $1 million. Your manager is going to ask you why. How do you answer that question? Why? Now that you know the math, you might get the intuition. Okay, I can ask you without giving the answer. I'll actually ask you, how do you know? Like, let's say your model actually predicted the house price as $2 million. Can you give me the reason why? How do you explain? How do you give an explanation as to why your model worked that way? If you can answer it in the chat. It's right here in the equation. The answer is right here in the equation. How can you explain why your model predicted the house price to be 2 million? There's no wrong answer. You can just shout out anything. Okay, features influence. That's right. So that is one answer. So what do you mean by features influence? So if you see these beta values over here, so these beta values over here, these are nothing but the weights. Now this is, let's say this is square feet of the house. This is number of beds. This one, what else is there? Okay, whether it has a kitchen or not. Now, if this value is, let's say 5, beta is 5, this one is 6, this one is 10, this one is 1. Now I know that my model is actually focusing on whether there's a kitchen or not. If there's a kitchen, it's giving more importance to kitchen. So that means if there is a kitchen, the house, it's going to say the house prices. It's going to give it. Basically, I can tell my manager that my model is focusing more on kitchen, more on the presence of a kitchen. If there is a kitchen, that means my model is more likely to give a higher prediction. I mean, not a higher prediction or lower prediction. The reason that the model gave this particular prediction is because it focused on a kitchen. The fact that that house has a kitchen is contributing more towards the prediction of the model. That is how I can explain it. And because you understood the math today, you will be able to explain it. That is why you need to know the math. You won't be actually coding math from scratch. But because of the fact that you actually know this algorithm works this way, you can go and give your explanations. So that is why you need to understand math on a very high level. I have seen Medium posts where people say, okay, there is a Medium post that says the reasons you don't need to know math to understand machine learning. I feel that's wrong. This is the reason that you need to know, at least on a high level. You don't need to, okay, there is, if people are familiar with optimization problems, there is much more to this than I explained. That is a deep level that you might need if you get into a research position or inventing algorithms. But until this point, at least you need to know to be able to better understand your models and tweak them. That's why you need it. Okay. Weights are the importance of features. Yes. It is sort of like weights are, it's sort of like importance of the features. You can, that's another interpretation. Yes. Okay. So logistic regression. Now, we've actually dealt with regression problems. We've actually dealt with house prices, stock market prediction, weather forecasting. That's all the stuff we've dealt with. But what about our Titanic survival? Titanic survival is based on zeros and ones. Can my regression model predict zero? I mean, my regression model, I can train my model, but will it give me exactly 0 and 1? It won't, right? It'll go, it's going to give me 1.2, it's going to give me 5, it's going to give me 10, 20, 0.5. It's not, it's going to give anything. Like it can be anything. So there is a way to convert the linear regression problem into the classification framework, and that is logistic regression. So don't get confused by this one here. So this is slightly confusing. This whole thing is still a classification problem. This is still this algorithm is used for classification, but somehow contradictingly, it actually has the name regression in it. The way it works is it works on the same equation that you've seen. This is the exact same equation from linear regression. So this is the same equation before. The only difference is there is a new function called logit function. If you see in the bottom here, this function here, it's called a logit function. What this function does is it takes this value, whatever value you get. So this actually belongs to the set of real numbers. So the result, not r plus, sorry, it's anything. This answer, this y value actually belongs to the set of real numbers. So you can get any real value. Now this logit function, what it does is it takes this value, whatever value you got, let's say 600 or 199.5, whatever value, and then once you feed it into it, this will only this f of x function will actually finally give you the result to be between 0 and 1. It will squash all the results and it will keep it between 0 and 1. Now this is what we want, right? So in case of Titanic, this is survived, this is not survived, and this is survived. So that is what we want. This logit function does that. So it takes all your real values and then squashes it to be between 0 and 1. That is what this logit function does for you. So it just takes this whole thing and then you apply that logit function, and it takes, this is what logistic regression is all about. From a mathematical perspective, it takes a linear regression equation, applies a logit function, and then just gives you the answer to be between 0 and 1. Now, when I say binary classification, I mean 2 classes. So binary classification means 2 classes. So when I talk about more than 2 classes, I have to call it multi-class classification for greater than 2. Otherwise, it's called binary. So in our case, for the Titanic survival, it's called binary because there are only 2 classes, not survived or survived. So essentially, this is logistic regression. So this is how it looks. So I just took the same equation. So I just took the exact same equation and I substituted the value here. So y equals f of beta 0 plus beta 1, so and so. And here I'm just putting, instead of this x, I'm just putting that value over here. Now, this is how I can define my final answer. So I haven't arrived at the answer yet. So I'm still going to get, so the value, the way that it's going to throw me these values is, let's say I take 199. If you actually implement it, it's very easy to implement. You can simply define a simple function called logit, and you can actually do it on your own. So I will show it to you. It's a simple Python function called exp. So basically, the values that you will get will be between 0 and 1. So it's not going to be exactly 0 or 1. So this f of x is actually going to be like this. So it's actually going to be between 0 and 1. Now, our class is actually defined as 0 or 1, not in between. So how do you do that? So this is one way of doing it. So you can define another function that actually says, if the value that I get is greater than or equal to 0.5, set the class answer as 1. That means he has survived. So in case of our Titanic, the person has survived. If it is less than 0.5, not survived. Now, why did I take 0.5? This 0.5 is sort of like a decision that you have to take based on your analysis, based on your outputs, your results, and based on the performance of the model. And this is also a business problem. So I'll give the example of fraud detection. Fraud detection is such a problematic thing that you only need one fraud to happen. If that happens, it costs the company billions of dollars. It doesn't matter if your model predicts things as not fraud. If it misses that one real fraud, it's going to cost the company a lot. So the way you can decide this threshold is based on those kinds of business decisions. You can ask your clients, you can ask your managers, do you want my model to predict more of fraud even when there is no fraud? So I just want to be safe. I don't want to miss out any fraud cases. I will make sure that my model throws out, even if it's not a fraud, I want my model to predict it as fraud. That's called false positives. We will discuss those metrics a bit later, but essentially I am instructing my model to predict most of the cases as fraud, even though there is nothing, just to be safe. Then what I would do is I would increase this threshold. So let's say fraud means 1, not fraud means 0. What I can do is, if I put if I put the threshold as 0.1, okay, let's say 0.2, that means anything greater than 0.2 should be 1. Like if I put it as much lower, let's say if I put it as 0.01, that means I'm just tagging everything as fraud. So that is how this threshold actually helps you in classifying these classes. So this is how logistic regression works. And the way that this function looks is something like this. So this is how it looks. So okay, it actually starts here. It goes like this and it comes here. So this is that 0.5 mark. This is actually 0. This is 1. This point is 1. So this point. So this point is 1. This is 0.5, and then this is 0. So this is how it works. So whatever is above 0.5, I'm marking it as 1. Whatever is below 0.5, I'm marking it as 0. So that's you can check it out. Logistic function, the logit function. This is how it looks. So that's it. Effectively, this is your first introduction to the most simplest algorithms, as we have to start our notebook. Let's actually summarize what we have learned till today. Machine learning is nothing but a set of algorithms where you actually learn from the data. Supervised learning is the class of algorithms where you have the ground truth. Unsupervised learning is where there are no labels. You try to find out what you don't know. That's what unsupervised learning is. You're trying to actually find out what you don't know. There is some hidden pattern in the data. You're trying to get that. Classification is nothing but, as you've seen, there is a finite set of outputs and you're trying to bucket your data into different classes. Regression is nothing but there are it's the set of real numbers. It's everything. You're trying to predict some real number out of all those different data points. Linear regression is an algorithm that's originating from linear algebra. Weather forecasting, house price prediction, these are all the use cases of linear regression. As you've seen, it's just that equation. You will roll in the parameters and then finally you make your predictions. Logistic regression is essentially linear regression converted into a classification problem. So sentiment analysis, Titanic survival prediction, even stock market analysis. Is the stock up or down? That's a classification problem. So this is a summary of what we have actually learned today. So are there any questions? We'll move on to a bit break. Real life. Okay, I'll answer some questions. Real life example of unsupervised learning. Okay, so okay, this is actually a real case. One of my friends, like when we were working on some projects, they actually did this for Toronto police. So what they did was they took neighborhoods. So neighborhoods in Toronto were designed, they were defined by certain set of features. So neighborhood means that particular neighborhood was defined by certain set of characteristics. They used clustering techniques to actually group different neighborhoods in Ontario everywhere into certain set of groups based on certain characteristics, so that the police could understand what's going on in different groups. Those different groups have different characteristics. They are exhibiting different characteristics. Their lifestyle choices, the way they are being fined on their parking tickets or whatever, it can be anything. So they took all this data set and they grouped these people into different categories. That actually helped them narrow down their scope of their problem. Now they can focus on different groups. Once they get into that group, they can subdivide it and again learn what's going on inside. This is one real life example of unsupervised learning. There are many, we will explore unsupervised learning, but this is one such example. It's just to group categories into different bunches. What is the difference between logic function and logistic function? I think both are the same. They're not different. It's just, okay, this is also called, there are so many names, it's just, I think it's the same thing. ReLU is usually, okay, we won't discuss about ReLU now. We will discuss about ReLU later when we get to neural networks, but okay. I think it's time for a break now. So it's 4:20. So let's come back at 4:30, 10 minutes. I'll be here to answer any questions.
Hey, Vyas, a quick question.
Yeah.
So for the cost function in the
let me share
optimization problem.
Yeah.
Can you hear me?
Yeah, I can.
Can you go to the graph, please, for the convex optimization?
Oh, the graph, okay.
So here theta is for every feature, correct?
Yeah, theta is actually a vector of all those features. So here I drew 2D because that's what I was limited to, but essentially it's all the features. Theta is nothing but the beta that I've drawn here.
I didn't get that. Sorry, theta is the?
So theta is nothing but these parameters. I just named it theta. Okay, that's a general convention, but it's essentially these things. So these ones. So the betas over here. So it's the same thing. Like maybe it's a bit confusing, but essentially this. I'll just a minute. Essentially, this is nothing but beta. So
Got it.
It's like this. So if I have three columns, then in three-dimensional space, this is how it would be defined. So this would be beta. Yeah, this would be beta 1, beta 3, and beta 2. As I keep changing these beta, I have to find the optimal combination of beta 1, beta 2, beta 3 such that I reach the minimal point.
Got it. Yeah, thanks.
Okay. Yeah, in this break, okay, you can take a break for 5 minutes, but make sure you upload all your notebooks and keep it ready because we'll be moving on to the next. So if you want to know, I have taken these slides from SlidesGo. It's very useful. It's nice presentations. So if you want, I'll share the updated presentation with all those drawings and everything if that's useful. Okay. Okay. Let's give 1 more minute for people to come back, and we can start. So I will post the answers to this week's assignment anyway soon. Okay, before we I have to touch upon one concept that I skipped last time. So zoom out. Okay, I have to discuss this first before moving on, because these things will keep coming up. Okay, I hope everyone's back. Okay.
Hi, are you still recording?
Sorry?
Is it still recording?
Yeah. Let me check. So Zoe Rohan is still recording, right? Just a minute.
It's recording on the screen.
Yeah, it is recording. Yes. I think so. I can see this small red dot. Yeah. Okay. So let's actually first cover some basic object-oriented programming concepts, as all the machine learning algorithms and all the other like I keep saying you initialize the object and so, like that's the reason that you need to be introduced to these concepts, so that everybody is on the same level. So object oriented programming is nothing but it's again like a framework. It's a class of techniques that are it's a okay, I don't know how to describe it exactly, because I haven't I forgot the official definition, but it's a kind of a concept that actually is helpful in designing your algorithms very well in a very structured format. So what's object-oriented programming? Object-oriented programming is made up of, I mean, on a very high level, there are so many other concepts, but these are the two most important things that you need to know when it comes to object-oriented programming. So classes and objects. So I will describe it in this way. A class is nothing, let's say a car is your class. So a class is nothing but a blueprint for designing an object. So let's say you have the general category of car is nothing but a class, and then the type of a car, the model, like the company and the model, Honda Civic, that's an object of type car. This is what classes and objects are all about. So you can have a single class called car, and then you can have multiple objects. Each object has its own characteristics. Honda Civic has certain characteristics. Toyota Corolla, that has certain other characteristics. Mazda CX, all these are different companies and different models of different cars. So a class is nothing but a blueprint for defining these objects. So let's actually see how to do that. So this is how we define classes in Python. So you say class, and then you define your class car, and then you set certain initial parameters, the brand, the model, and then the stick names: path, drive, reverse, speed, control, neutral. Now within the class car, I can define multiple functions. If I say ignition, that means I'm actually going to start my car. If I say stick, that means the position of my stick. You can see how object-oriented programming allows you to actually model real-world objects in programming. Most of software engineering projects are done using these principles. And it's very good. Like it's in such a structured format that I'm actually able to visualize my car and having a function called ignition and having a function called stick. That is what the object-oriented programming essentially is for. So finally, if I run this code and if I create my car object, car Honda Civic, so that means inside this, finally, I'm going to have, if I actually check my car object, if I say dot, I'm going to have stick and ignition. And if I say brand, I'm going to get Honda. So this object has a particular attribute called brand. It also has an attribute called what is that? Model. So these are all the different, it also has different functions. So let's say ignition. Let's call that actual function. So my civic is off. So how do I say on? I provided the parameter. So I'm just going to say on. So my civic is on. I just started my car. You see how I'm actually able to model real world objects in programming. So this is what object oriented programming means. Whenever I say initialize an object, that means when I call this car, the first thing that happens is the moment I call this car, the program actually goes here. It actually executes this function by default. So let me actually prove that to you. I am here now because you called me. So let's actually run car now. Okay, you see this? Why did this function get called? Because the moment you do this, it's actually going to go here and execute this. So when I say initialize in machine learning as well, when you actually create a function called linear regression, all this kind of a function is actually defined somewhere in the code and it's being called to set the default parameters. Then inside that you have multiple different functions that you can execute. So this is just a quick introduction to object-oriented programming that I wanted to touch upon. If there are no more questions, I'll move forward. Okay. So before I begin, I hope you all have already loaded your notebook. It's called ML Bootcamp 21 week 2 intro to ML. And then there are 3 CSV files: test, train, test, and then social network ads. Just let me know in the chat by saying yes if you already have all this uploaded. Okay, that's great. So most of you already have loaded it. I'm sure, thankfully, all that's done. So that's good. So now let's actually start. Just minimize this. Okay, I'll close this. So the first thing to do is, okay, whenever you program like in Python, it's a good practice to have all the import statements at the beginning so that they're not scattered anywhere in between. So like this is one place that these all are good practices. There's no rule that you have to follow this. If you see some of the notebooks in Kaggle, they can have somewhere in between, they might have defined some kind of import statement somewhere in between. You can still do that. This is just a good practice because whenever I want to import something, I have everything ready over here. If there is an issue, I know exactly where to go. If there is an issue with importing a package, I don't need to search through my entire code. Where did I import it? I can go right at the top and see that I've imported it here. That's why it's a good practice. So I've imported pandas. I've imported NumPy. Now scikit-learn is the package that you are going to be using mostly, and this is it's actually a good idea to go and visit this package if you want to. So you can just search sklearn Python, just search that, and then the first website that you see is scikit-learn.org. So this is an open source website, and it's an open source package that actually provides all implementations of all the algorithms, and this is maintained publicly. So this is an open source group, and then you have like you can just install scikit-learn very easily. Like you can actually learn machine learning just from this website alone. Like they have everything. Like you get into classification, you have all these methods. So today we learned about ordinary least squares. Let's get into that. So you see the diagram is right here. You can actually learn so much about machine learning right from this website. So they will show you exactly how to implement it. They will show you examples, and then they will show you all the different kinds of classifications along with the most basic math that you need. So this is a very good website, and I would encourage you to just explore this website whenever you have time. So because that is what we've imported here. So what I did is, these are import statements, but let's say scikit-learn is such a huge package. It has so many things. From scikit-learn, I want to get specifically linear regression. That's specifically what I wanted to get. So now, because from scikit-learn I wanted to fetch linear regression, I said from sklearn.linear model. So that means within sklearn, I use the dot operator to again further fetch the actual class called linear model. So if you remember this, this is how I'm calling it. So it's exactly the same thing. So I'm saying it's not exactly the same thing, but it's something similar. The notation is the same. So I'm saying sklearn dot linear model import. Now I'm going to import linear regression and logistic regression. All this documentation is actually available here. So if you go here, if you check for ordinary least square, you see this. From sklearn import linear model dot linear regression. It's exactly the same thing that I did. I did from sklearn dot linear model import linear regression and then logistic. sklearn also has metrics. It has something called classification report that I will show you. Mean square. It has all these metrics defined. It has techniques to split the trained data set. Forget this for now. We'll introduce this later. There are different pre-processing techniques and then matplotlib that you've seen before. So now I've cleared that out. I've explored. I've imported all the libraries that I want. That's done. Now let's move on to some. So I haven't done much exploratory data analysis here because next week we will be covering something called feature engineering, and that's when EDA will actually help. For now, I've done minimal exploration data analysis. So let's start with the most basic thing. Let's actually first create our data frame. So what's happening here is this is a class that has a function called read. It's exactly the same thing. It is a class that's calling a function called read CSV and passing in the parameters, and an object has been initialized. So if I try to run it, okay, this means I have not run the first cell. So name PD is not defined means I have actually not run the first cell. So this is the reason that I asked you to import all the statements in the beginning. I know exactly where to go. So now that I've imported that, let's actually print this df. So this is how df looks. For the sake of simplicity, I just chose one variable to understand linear regression. In case of that house pricing problem, there are so many other x variables, x1, x2, x3, x100, like there's so many. For now, I've just chosen one variable. So this is the x variable that you've seen, and this is the y variable that you've seen in the slides. So let's actually look at the shape. So there are 700 rows and 2 columns. So to look at the first few rows, this is what you get. So x is some value, just some value 24, and then y is some other value 21.54. So let's check for the null values if there are any missing values. This is the most common way to check that. So you say df dot is null. So let's actually just do df dot is null. This is going to give me, if there is any null value, it's going to give me true. Otherwise, it's going to give me false. When I add this dot sum function, it's going to sum up all the true values and give me. So in y, so this means if I say is null, somewhere in this y there is one value that says true. That is what is being picked up by this sum. So this is a nice shortcut to quickly get the number of null values. So this means that y has one null value, x has 0 null values. So how many of you so how many of you think I have to drop it, and how many of you think I have to fill that null value? You can just type it in the chat. Okay. Yeah, actually it really depends, but let's drop it because majority of you are saying drop. But I will also show you. Okay, filling is imputation. Yes. So okay, so basically what happens is we will do this later. I haven't touched upon one concept in the slides. There is a drawback of linear regression. You will understand that drawback right now. For now, let's just drop the value. I will repeat the same experiment by filling in the value and see what happens when we fill. There is going to be such a drastic difference that you will know that cleaning null values is so important. So for now, let's just drop the value. So after dropping the value, I'll actually tell you when you have to drop, when you shouldn't drop, when you should impute, when you shouldn't impute. I'll tell you those differences. So let's check is null.sum again. Okay, it's clear. Now I don't have any null values. The reason we have to remove it is because machine learning algorithms cannot work. Some of them can work with null values, but some of them cannot. So now Okay, there are some Masha asked the question, what would be the reason not to drop it in this case with 700 rows? So there are some reasons when you shouldn't drop. So basically, if your data set is, so machine learning algorithms only work well when you have lots of data. If you start dropping everything, the model will not learn anything. Now this is just one value, that's okay. But in certain cases, you have to decide really whether you want to drop them or you want to fill them. So I would say, okay, this is not a rule, but it worked out sometime for me in the past. If more than 70% of a given column is missing, you can just drop it. There's no point of having that column. But if only few so basically, if only a few of the values are missing, then you can actually go to filling in those values. How do you fill them? Based on, like, let's say there are certain basically techniques that allow you to fill up those values. They are already present in these algorithms, like method, backfill. Basically, based on the previous value, it will fill up the next value. So those are already there. This is only one, there's only one x value. Let's say there is x1, x2, x3, x4, x5, and the feature column x5 has 90% missing. Like there's nothing absolutely. So you just drop it, blindly drop it. There's no point of training the model. But if like 30% are missing, then maybe I can replace them by some techniques like replacing all the values with the average. That's one common technique. You just replace all the values with the average value of that entire column. That's the most simplest technique. So I will share few articles on how you have to drop it. But in this case, when I was actually preparing this notebook, I've noticed a huge difference in these two things. I will show you that. And that's one drawback of this linear regression, which I will explain because of that. Okay, so now we are actually ready to deal with our model. So let's actually first visualize our plot. So I'll just zoom out a little bit to view the plot better. So let's take all the x values, let's fetch all the x values. So this is why I asked you, this is why you have to do the assignments using pandas. Everywhere I will be using pandas and numpy and nothing else. So you have to get used to these libraries. So if you see what I did here, I actually selected the x column from my pandas data frame, and then I converted it into a numpy array, and then I fed it into xtrain, because that's how you need to feed it for these functions to run. So all I did here is df of x. So let's actually run df of x. If you see this, this is df of x. So all I did is I wrapped it inside a function called np.array. What that function does is, this is a built-in array function. So it converts this series, pandas series object into an array, and then I'm just plotting it. So I use plt.scatter. So if you see this matplotlib, I've imported this. Okay, this particular pyplot library helps you to plot histograms, bar charts, pie charts, and everything. So that's what I'm doing. I'm taking this PLT. Inside that, I'm calling a function called scatter, and I'm providing the x-train values, y-train values. This is just to adjust the figure size. I'm saying 15 inches by 10 inches or whatever scale it is. And then let me zoom out a little bit. So this is what it's printed. So this is our problem. So if you remember the slides, this is exactly what we have. These are all the dots. For different x values, we have different y values. For 60, we have something. For 80, we have something. For 24, we have something. What is linear regression going to do? It's actually going to draw a line for us based on the data. How does it do that? Now this is how we do it. So if you remember, we've imported linear regression. So call the class linear regression. So that's why it's important to understand object-oriented programming concept. If you see this define init, do you see why I got define init? Because that is the first function that will be called. If you remember the car example, this is the function that's being called. If you hover over linear regression, you will see that you will see define init. So when you call this function, this is the first step that will be run. All these parameters will be initialized, and then just like I have called ignition, there's a function called fit. Now what happens is, yeah, I have taken only 50 values here because it got too congested. So if I actually take the whole thing, so someone asked, so if I actually take the whole thing, it's not that visible. So wait. Oh, I didn't run it. Sorry. That's okay. I mean, I thought this was not that clear, but yeah, I just wanted to show a clear example. That's why. So these are all the values. So okay. Now basically you initialize the model linear regression. This is what you will be running always to run any model. Every model in scikit-learn, this is how they define it. They define some class, some kind of machine learning model called linear regression, and then they define a function called fit. This means in this line, the model actually went through each data point and it's learning those parameters. It's actually running those functions inside. All the math that we have seen till now, it's actually running it inside. We don't know whether it's using gradient descent or not. I haven't checked their implementation, but okay, linear regression to minimize it. Okay, I haven't seen how scikit-learn actually implements it, but if you go inside and see, they have done something. Either they have done ordinary least squares, or they have done gradient descent, or the matrix inversion, or something. Okay. Okay, Rohan says it's closed form solution. So yeah, it really depends on the like if you want gradient descent, you can implement it. If you want the single closed form solution, you can do it. But essentially, this is what happens. So sorry. So now that I sent fit, inside the fit function, you have to call these two. So when I say dot fit, I mean I have to provide the x train as the first argument and then the y train as the second argument. We did not split the data set in this case. We will do it in the next part. We did not do it here because I already have train tests separately. So I don't need to split anymore. This is not the case in general, but in this case, luckily I have the separated data set already. So just say fit, now run this cell. Now what happened is in that instant, the linear regression model just learned this entire data set. It actually learned the whole thing. It knows it actually ran. Okay, for the sake of our session today, assume that it's gradient descent. It just ran that entire gradient descent algorithm. It found the optimal point, and then it got you those beta values. Once in this case, there's only one beta value because there's only one variable. So now that it learned that, okay, let's actually get the test data set. So get the test data, get the test data set, get the test x values, get the test y values, and then get your predictions. To get your predictions, you just need to say reg.predict. You need to provide the x test. So you need to take your x values are the input, then you have to say predict, and then you get the y values. Okay, reshape. Thank you. So Masha just asked, what does this bit reshape do? That's a good question. I just skipped over it. So basically, if you remove reshape, just try to remove reshape. So it's not going to run. The reason is the way that linear regression has been defined internally in the code is that they expect you to provide a 2D array. This is giving you a 1D array. So what this reshape does is it reshapes the 1D array into a 2D array. So it's the exact same thing. So let me show you. So this is x train. You see, focus on this single bracket. Try to focus on the single bracket. Let me say reshape. Now see, there is a double bracket here. This has become a 2D array. Okay, if you see, there's a two square brackets here. It's actually become a 2D array. Reshape basically takes any array and reshapes it into this dimension. So that's essentially what it does. Okay. Yes, it's reshaping into a 2D. -1 means -1 means okay. So finally, I want I don't know, like what I'm saying is -1 is to indicate that I actually don't know what the dimension I want. I know that the second dimension has to be 1, but I don't know what the first dimension is. So I just left it as -1. I'm assuming that the function reshape will take care of it. So if I don't, I know that I want it as 2 by 1, but if I just don't know what it is, I just leave it at -1 so that it will assume on its own whatever it is and it will give me the right shape. That's why if you're not still clear, I would say read the documentation, but this is the reason why we need -1, 1. So let's actually run it. Now let's actually start predicting it. Now let's check the predictions. So before we check the graph, check y test. So y test are these values 79.7. This is the ground truth. This is the actual values. Now check your model's predictions. Okay, these are the predictions. So if you remember, the first value was 79 in y. P got 76. The second value was 18 or something, and this is 20. So your model actually learned very well. So let's run that. So this is the best fit line that we got. So the model, let me zoom out a little bit. So now the model has actually learned these data points and then just got me the best fit line. That's what I did. I printed the scatter plot of the ground truth values, and then I plotted the best fit line using model predictions. So the red line is actually our predictions, our model's predictions, and then y test scatter plot is the ground truth. So because this is linear, this is a linear regression algorithm, this is the bias in the model. It always works on the assumption that the data is linear. Like, it always gives you a straight line. It is linear. That's it. There is no, you can't have a curve that touches every data point. That's a non-linear one. This is completely linear. So this is how it works. Okay, now let's get to the missing values. Why I am actually saying missing values is so important. I discovered this when I actually was preparing this notebook. So let's actually see. Let me run this whole thing again, but this time I will do the other one. So we have a missing value. Instead of dropping, I'm going to comment this one and uncomment this one. Run the same thing. Just don't change anything. Just keep running this. Okay. You see, where is that? Did you see that where that actually the filled value went? This is the filled value. This is that missing value. So all the data points are here. The missing value actually came here. This is the missing value. Now, what do you think will happen? Before I show you the curve, what do you think will happen? Can someone describe in the chat, or you can just shout it out if it's too hard? How do you think the line should be now? How do you think you'll get the line before I go down? Will I get a straight line across this?
It'll be biased towards the outlier.
Exactly. So that's one problem of a linear regression. So what happens is, if you remember the concept, it checks the distance between every point and every line. It also checks the distance between this. So the line is pulled so much towards this outlier that let's actually see what happens. So let me run the whole thing. Okay, did you see what happened? So the line actually got pulled towards this data point. So basically this is what happened. Like it just got stretched towards that point is somewhere outside this graph. Like it's completely outside. So it's somewhere in 3500. So it's not even there here. So this is one reason that missing values are so important. You actually saw the difference right now. So that's why dealing with these missing values appropriately is a good this is very important here, right here. So I hope you understood that. Because when I designed this, I actually didn't understand why this happened. I actually, honestly, I didn't understand why this, because I knew that the model was very good. It was so simple, yet I got this line. When I saw this graph, I understood that it was because of this outlier. That's the reason. Those are called outliers. So these are actually called outliers. So I'll just write it down here. So these are actually called outliers. Yeah, this case, okay, in this case, my model, okay, in this case, it's just one outlier. That is so strange. It almost makes me believe that that's a wrong observation. Someone in their records have noted something wrong. It can't be the case that I have 100 good values and one is missing. So that outlier is so strange that I'll just omit it. In this case, okay, it is my independent decision that I will omit it. If you feel that that's actually worth exploring it, you have to go and explore that value. That's all. But in this case, I would omit it. So Eric is asking, how does backfill work? So you can explore the scikit-learn documentation. Essentially, backfill means it looks at the next value and predicts the previous value. So it looks at the next y value and it tries to impute the previous value based on the pattern. Somehow it didn't work out here. Okay. So how do we evaluate our model? So in regression, there is no such thing as accuracy. How do you even get accuracy? Let's say I have something like this. So let's say let's say my ground truth is 0, 0, 0, 1, 1, and my predictions are 1, 0, 0, 1, 0. So what is the accuracy? Accuracy is nothing but how many I got right. So I got 1, 2, 3, 3 out of 1, 2, 3, 4, 5, 3 out of 5, which is 60%. So my accuracy is 60%. But how do you do this in regression? It's not, if you try to do accuracy here, obviously you will get 0 because no value is ever going to match any value here. Like if you see this line, no value is ever going to match any of these values. That's why in regression, there is something called mean square error. So it's the same formula as the cost function. The mean square error is it's the exact same thing as the cost function. It's the error. So mean square error is nothing but you're taking the y-test, you're subtracting every y-test from your prediction, you're squaring it and summing it. So if you get a low mean square error, that means the difference between your values and your ground truth values and your prediction values are actually they're close to each other. That's how mean square error is used. There are other techniques: R2 score, mean square error, mean absolute error, root mean square error. So that's how you evaluate regression models. This time it is so Eric asked, is it a good thing that we dropped? Yes, actually it is a very good thing that we actually dropped it, because you've seen, like, this is such a bad line. Like, okay, my predictions are going to be right here, no other prediction is going to be right. So this time it's a good thing that we dropped, but otherwise, yeah, there are different articles that you can read. This is one way that I dealt with this outlier. There are so many other techniques. We can explore them later in feature engineering. So did you all understand? Are there any questions regarding linear regression? Because I'll be moving on to the next one now. So if mean square error is high, how do I actually improve the model? This is why I keep stressing feature engineering. So feature engineering means, based on the data, we have to actually somehow tune the parameters, or we have to get new features. This is such a simple model that it has only one variable and you can't do much. So the only thing I can do is check these parameters. So normalize, it says normalize false. Let me try normalize true. So I don't know what's going to happen. Let me just try it. So you have to adjust these parameters. So you don't just rerun the model, you rerun the model with different parameters. You test different parameters and see what's going to happen. Okay, let me remove this. This outlier is causing a problem. Let me remove it, right? Okay, we are back to our good line. Let's run. Okay, it's still 9.43. It is high. The line looks good, but somehow it's still high. You can try out different techniques, and you can, if you have more features, you can basically, feature engineering means basically trying to modify your features to get a better score. So mean square error should be low. It's 9 means there is always room for improvement. That means I have to do something. I have to do parameter tuning. I have to, maybe linear regression is not a good approach. There are there is a class of algorithms called decision trees. You can do regression with them as well. There is support vector machines. You can do regression with them as well. So this is not the end of the road. It's just one algorithm. So either you improve the parameters of this algorithm or try out something else. So that's one way you can improve them. So there is no high. So there is no such thing as a high mean square error. I am saying it's high because let's actually take, there is, it means, this is actually mean squared error. So if let's say this y values represents the height, let's say let's say the x values are weight and the y values are the height. Based on the weight, you're trying to predict the height. It doesn't make sense to say height squared. So what I'm going to do is I'm going to take the square root. Okay, there is no square root function. Okay, I just tried something. There is a library called math. Inside math, there is a function called square root. So let's do root mean square error. So math.qrt. Okay, this makes sense. This means it's telling me the average difference between my value and the true value is 3. So I'm always off by 3. That's okay. That's one interpretation. I can use np.square root. That's a good point. I forgot about that. Yes. So basically, there is no high. There's no definition of high, but essentially, if you can get it below 0, that's like very good model. You can, I mean, just think about it, right? If you have some value, let's say this value is 40 and you predicted 39.999. So what's the mean square error over there? 40 minus 39.999 whole squared. That's such a less value, right? That's the mean square error. So if you get a very high value, that means, let's say for 40, you actually predicted the value as 100. So it's 100 minus 40, that's 60. 60 squared, that's 3600. That's such a high value. So that's how you judge these things. There's no defined a high value. It's just based on your intuition. But essentially, this is a good score. I would say I'm off by 3, which is fine. If I can get below 0, that's even better. A good range, maybe like single digit numbers. Don't get double digit numbers. Yeah, the R2 score is good, but okay, R2 score doesn't necessarily give you, okay, R2 score is basically, it does explain maximum variability, but you also have to explore other metrics as well. Okay, right now you told me R2 score is 98%. In the chat, Masha said R2 score is 98%. But I can clearly see that the mean square, if R2 score is so high, the mean square error is still 3. That means that's the room for improvement that I'm talking about. Even though the R2 score is high, there is still a room for improvement where the mean square error it tells me that if you see the first values, if you see y test, the first value is 79. Let's look at model predictions. The first value, it's 76. I just showed you that the value is off by 3. So that's the root mean square error. That's on average, it's off by 3. So that means there is still room for improvement. But this is actually a very good model. That's why you should check R2 score, mean square error, root mean square, everything, and then judge your models. So the way we can improve this, one way to improve this is just by throwing more data. That's it. Just by throwing more data. Just keep throwing more data and then just getting everything. So I will move on to logistic regression for now. I'm sure there are much more questions. We will deal with them a bit later, but yes, I will at least move on to logistic regression for now. So actually, Hussein brought up a good point. It's based on bias and variance, and that's a whole different concept that I have to talk about a bit later. And that's actually very key to understanding these performance metrics. Bias and variance is a very good topic that I will be covering later. So I'll move on to logistic regression. Now make sure you have this data set, social network ads, CSV. Let's read that, just check the shape. And now after checking the shape, let's actually look at the first few data points. So we have user ID, we have gender, we have age, estimated salary, purchase. So now just by looking at this, I can tell you that it's just it's somebody with this much salary and this much age just purchased, whether given the age and salary, whether they purchase products or not. That's all this data is all about. Let's check for null values. Okay, we are lucky today. There are no null values. So that rarely happens, but if it happens, it's good. Now let's see how to actually split the train test data set. So here you see this, you can see it right here. So this function train test split, it is provided by SQL. It splits the arrays into random train and test subsets. That's the advantage. It randomly picks data points and splits them into train and test. How do you know the first one is xtrain, second one is xtest, third value that it gives us is xtrain? I just look at the documentation. You just hover over this, scroll down, and they will give you the implementation right here. So you just take this. But initially when you're learning, try to type everything. So essentially it's giving me a tuple. It's giving me a tuple of 4 values. Those 4 values are xtrain, xtest, ytrain, ytest. So now I'm not going to use gender for now. Let's stick to the quantitative numbers, because to use gender, you actually have to convert. Okay, you have to convert male into a number and female into another number. You can't feed strings into machine learning models, because ultimately machine learning models, they need numbers. They can't work with strings. That's called one-hot encoding or categorizing. We will learn about that. If we have time today, I can show you that. But otherwise, essentially, let's stick with all the numerical values for now. So I've selected age and estimated salary, and then this is the X. Now this is the Y. So the Y is nothing but the output, whether purchased or not. Test size is 0.1. Now test size means I am saying 10% of the data is test, 90% of the data is train. How did I decide this? Based on this. There are only 400 data points. If I say the test data is 0.5, if I take 50% to test, then I only have 200 left for training. That's so small. So I want to make, because the data set is small, I want to make sure I have much larger amount of training data set. That's why I chose as 0.1, which is 10%. So if you, okay, I'll zoom in a little bit. Focus on these double brackets. So in pandas data frames, when you want to basically when you want to select 2 or more columns, you use double brackets. And then you just, inside one bracket, you put another bracket, and then you just type the number of columns. I mean, the name of the columns. So once I did that, again, same story. Define the class, get regression, and then just say dot fit. This is not the end of machine learning. It's not that you can just keep doing, you can just take any machine learning algorithm, just do dot fit. There is a lot more to do after this. Once you do dot fit, you will actually check the performance. Sometimes it may fail, and then so Rohan, someone is waiting in the room, just to let you know. TBS, not sure. Okay, so basically logistic regression, this is how you do it. For every algorithm, you just do the same thing. If it's SVM, you just say SVM, and then you just do dot fit. For the procedure is the same. That's how scikit-learn did, but there is much more to it than just doing dot fit. Understanding that math and then doing all those other things will actually help you improve these models. So now that I've done xtrain, ytrain, and fit, let's actually split the data from this. Okay, now let's predict it, and then now I'm going to use classification report. So classification report is a function by scikit-learn that gives me these 3 metrics: precision, recall, F1 score, and accuracy. So I'm going to run it. Oh, I didn't run this one. Okay, this is a very bad model. Can you tell me why? Okay.
Because it doesn't predict y values. It only predicts zeros.
Yeah, exactly. So this is not that great of a model. It only predicted 0, and it didn't predict 1 at all. Before I move on, Eric asked the question. 1 minute. X variable. Okay, the X variable is actually, there are 2 variables here. So we have X1 and X2. This is Y. So there are 2 variables this time. Last time we had 1. Now we actually have 2. So X1, X2, and then Y. So X actually consists of 2 variables. Okay. So now let's get into this. So can anyone tell me what is the reason? Why is the model behaving this way? Can you guess what's the reason? Like, why did it say 0 everywhere? Like it's not even, if you check the predictions, let's actually check this variable social prediction. It's all zeros. Why? What's happening inside? Yeah, because of training data, but why? What is the reason inside? What happened inside the training data?
Is it the split? Did you have to do something else for the split?
So maybe, okay, let's check the white train. So white train 2, okay, we have zeros and ones, that is fine. Let's check white test. Okay, we have zeros and ones, but I'm still not able to figure out what happened. So I'll tell you what happened. So someone already gave the answer. In training data, most of purchase, yes, exactly. Okay, so in training data, most of the purchased is 0. This Rohan gave the answer, so it's called class imbalance. So how do you check that? So that's the most important thing that I haven't checked here, and that's actually so important that is the first step that you always have to do in classification problems. That is one of the first steps that you have to do. Once you get sample and shape and all that, the next step that you have to do after the null, I mean, here you can do that here. So just say df. Okay, now you will know why I asked you to do the assignment using value counts. So value counts will actually help you here. So the value counts function, if you remember from the assignment, so what is the data frame? Social. Okay. Purchase, I'm going to select purchase, and then I'm going to say value counts. Okay. Now you can clearly see that it's not bad actually. I mean, it's not such a huge class imbalance, but still there is imbalance. So what I mean by imbalance is this. So class 0 has 257 and class 1 has 143. This is the imbalance. That's the reason that the model is biased towards predicting all zeros. It's just getting all zeros. And then what happened was the split. Yes, the split function did not take care of it also. So as you said, the split function also caused some trouble. So maybe let's look at the value counts inside this. So let's check train purchased. Where did it go? Where did it go? Okay, here. It is 233, 127. Okay, so in the split also it got imbalanced. So there are 233 zeros, and now let's check the test. Okay, there are 24. It's still imbalanced in the test and train, but it maintained that ratio. So how do we improve this? Like, what are the what can we do here? Like, what do I need to do? So in okay, so does anyone have any idea what we can do here? Okay,
Can
yeah,
we force it to do 50-50? Sorry.
Sorry?
Can we force it to be like 50-50 kind of?
Yeah, but how do I do that? I would have to drop zeros. So in order to force it to be 50-50, 1 is actually very less. 0 is actually very high. So I would be forced to drop some zeros to actually make it 50-50, or I would have to artificially create ones. There are techniques to deal with it. So it's called class. So there is something called upsampling and downsampling. Downsampling means this is known as the majority class. Majority class is the one that has higher numbers. Minority class is the one that has low numbers. Downsampling means I'm going to cut down 24 and make it so that it equals this, or I'm going to artificially generate new data points manually. Like it's easy, right? Like it's just an age. If I have 41,65,000, I can make up another data point. I can just say 41,55,000. So like that, it's artificially going to create such that the 16 matches 24. We can do that. That is one way of dealing with this, or stratify. Like Nia said, stratified sampling is one more way. This one is already taking care of stratified sampling inside. Stratified sampling is nothing but making sure the distribution is the same. So if you look at X train, sorry. So if you look at X Y train underscore 2, this is 233, this is 127. So what is the percentage? So it's So it's 233 divided by 233 plus 177. So that's 56%. Now let's actually take the test. So that's 24, 16. Oh, I could have done that in pandas actually. Anyway, so okay, if you saw previously it was 59% and now it is 60%. So it's essentially the same thing. It's already stratified. Stratified means the ratio of the classes is kept the same. So this is 60%. The previous value was also close to this somewhat, 56%. So this is stratified sampling. It makes sure the distribution of the class is the same. How I would actually improve this is there is something called class weights. So listen to my argument and let me know if this sounds logical. What I am going to do is I'm going to penalize the class 1 mistakes more. I'm going to say it again. What I'm going to do is whenever my model makes a mistake on predicting 1, I'm going to punish it more than I'm going to punish it when it predicts 0. This is known as class weights. So what I'm going to do is there is a parameter here called class weights. If you see this, if you hover over logistic regression, you will see something called class weight. So everybody, you can follow along with me. Just say class weight. It's a dictionary where you have to define the class weight. So I am going to say focus more here. So let's say I'm going to say 0.6 and that's all. I'm not going to do anything else. Focus more on 0.6 and then maybe focus a bit less on class 0. So I'm saying focus more on class 1, focus a little bit less on class 0. Now there is no defined number here. It's up to you. You can put any number here, but I'm just okay. Let me assume that the total sum. Let me assume that because it is 2 classes, I'm going to make sure that the sum of both the values is 1. I mean, there might be rules as to how to define this class weights. I haven't gone through the documentation completely, but I'm sure there should be something. Yeah, you have different rules. You can use them, but this is what I'm going to do. For now, I'm going to say that use class 1 for punish if you remember the cost function formula, give more weight or basically make the loss higher for class 1 so that it will learn much better. Let's actually run this and see what happens. So predictions. Okay, now it actually went the other way. So you have to adjust this class. Actually, I did it already. Let me actually try. Yeah. We have to just, these are the hyperparameters that you need to tune to improve. I'm making it more costly to predict 1. So I'm penalizing 1. So what I'm saying is whenever you make a mistake with 1, you are punished more. So your loss is actually much more than you are already calculating. So adjust your weights much better. I'm saying focus on 1 simply. That's what I'm saying, Hussein. So I actually did it yesterday. I don't know why I'm not getting it. So I should have saved it. Okay, yeah, basically try to adjust the class and somewhere you will arrive at exactly what you want. I was sure that I did it as 0.5. Okay, let me just put it as 5. Yeah, it's a hyperparameter that you need to tune properly. And yesterday, believe it or not, I actually got 90, 89, 90, 89, 90, 79. I actually got a very good model. I'm somehow not getting it now. But otherwise, class weight is one way to deal with it. The other way is upsampling, downsampling. You can definitely try. So now let's look at this. This is how I can visualize it. So let me zoom out. So basically, this is the ground truth. So Seaborn, I'm using Seaborn's library to say this is the data, this is the X value, this is the Y value, and hue. Hue means use the colors according to purchase. So if it is 0, it will paint it as orange, and if it is if it is 0, it is painted as blue, and 1 it's orange. So you can see this is the decision boundary. You see this thing here, this separation. So this line here, this line is the decision boundary here. Now let's look at the predicted value. Obviously, it's going to be very bad there is everything. It's predicting everything as 1. Obviously, there is not. It's not a good model, but otherwise you should see something similar to this. Let me just try it. Wait. I don't know if any one of you figured it out, but I forgot what the values did I put here. Okay, it's not there. I'm not getting it, but otherwise you should get it with. There are techniques to do hyperparameter tuning. This is not how you do it. You don't manually sit and do 0.9, 0.6. There are well-defined techniques to do it, but otherwise, this is how you actually finally. This is what you do in machine learning. Like in practice, this is the first step to as your introduction to machine learning. So scikit-learn is a good library. You can read the documentation, you can understand a lot from it. Essentially, that is how you call these models and then train the models and then predict them. And finally, you check these scores. Now, how many of you are familiar with these things? Precision, recall, and accuracy. Just say, you can say yes or no. Okay, so I'll describe what,
yes,
since we have a lot of time. Yeah, okay.
Yes, I have a question. I wasn't able to understand that weight part. What is it exactly doing to that model? Is it adding values to create a loss, or what is exactly happening there?
So this weight, maybe let me share this. I'll share this. I'll show the slides also. Then it can be clear. Just a minute. Okay. So here, if you look at let me go to the, where is that? Okay, this is the cost function. Right now, what's happening is basically, okay, logistic regression has a different cost function, but otherwise the concept is the same. There is a cost function, some gradient descent is happening, it's subtracting these weights. Now, if I increase that weight, if I say class weight, if I say increase the class weight of class 1, that means I am saying whenever there is a mistake means whenever I am off, whatever you are subtract more, or basically penalize it more. Make sure the cost function is much more than what it is. So what I'm saying is, if I put a class weight of 5, that means what is the objective here? The objective is I have to minimize this thing. The main objective is I have to minimize this difference. Now what, instead of this, let's say I have plus 1, let's say I have plus 100,000. Is this going to take more time to minimize? Of course. Why? Because I have plus 100,000. I'm supposed to even minimize that number. That is how weights work. So basically what I'm saying is, instead of minimizing this one, minimize this plus minimize the attached weight also. So that means if the cost function, if let's say when I'm predicting class 1, the difference, the error is 5, I don't want you to assume that the cost function is just 5. I'm saying it is 5 plus some other additional weight. So I'm saying the cost function is actually much more than what the cost function actually is in the formula. So that's how I'm saying whenever it is class 1, the cost function is actually much higher than what I expect you to do. And then that way, this beta will actually be penalized much more. So beta will actually be much more careful when it is actually predicting 1. By careful, I mean that it will predict it much better. That's how that weight thing works.
Got it. Thanks.
Yeah. Okay, so someone got it. 0.7 and 0.6. Let me try.
Yeah, I didn't get it correctly, but it split them at least between both of them. It's still 81 and 29. I was just like trying to play around to get something that gives both sides a number.
Let's see. Okay, okay. It's totally random. It might not work for you.
Oh,
okay, you see this. Okay, this is an important one. So the one that you ran has a different random state than what I have. So this random state is what causes different answers. So if you define one single random state and I define the same random state, I'm going to get the same values because there is some randomization inside in that algorithm. So another important point that I actually did not touch upon is actually called regularization. So regularization is actually a very important key concept that I haven't touched upon yet, but we have time, so I can touch upon that. Regularization means in this cost function, just like the weights, in this cost function, apart from this cost function here, it is a technique to actually make sure that basically the model performance can improve by not allowing it to overfit. So I'm getting much too technical into these machine learning terms, but essentially regularization is a technique to help the model generalize much better. So this is how regularization can look. So this is the cost function. When you add the term called regularizer, what happens is, okay, I'm just inventing terms. There's nothing called regularizer. It's called, the technique is called regularization. Let me actually write the equation. So it looks something like this. So it is that symbol. So it's okay. It's basically lambda, and then it is lambda beta square. So this is how regularization looks. Okay, so this is one way of regularizing. There are other ways, like people also divide it by 2 and then something. So by adding these terms, what happens is I am actually making sure that the weights are not exploding. So what happens is, another way to improve this model is, let's look at this column. So if you see, estimated salary is so high, like it's 65,000, 77,000, 100,000, 30,000, and then age is so low. They are on totally different scales. How do I now what happens is, if I don't have regularization, or if I don't scale them, the weight, the beta value for estimated salary is going to be very high, and for age is going to be very low, and the model is going to be biased towards salary because this value is already high. They're totally out of scale, out of proportions. So for that, I actually imported this standard scaler. So what happens is, basically both are brought into the same scale. The simplest standard scaler is nothing but subtracting it with the mean and dividing it with standard deviation. That's a way to scale these things. That is something that happens here. So what happens here is, basically it's penalizing the weights. It's making sure. So okay, this is how you should wrap your head around this cost function. If the cost function is high, it will make sure the weights are low. The purpose is to minimize this cost function. If I have high values here, the algorithm will work in such a way that I have to reduce the weights. This will ensure that the weights are not exploding, and it's not giving too much importance to one feature and not the other. So that's the concept of regularization. Please read about that. As if you just see this C parameter here, this C parameter actually controls regularization. So you can do that as well. So let's actually try to introduce C. Let me say it's 0.7. It's still not working, but essentially that's what this C does. It's a regularization parameter. So okay, Jerry gave me some answer. I don't think I'm going to get it today, but that's okay. Let's just leave it at that. Hopefully, if it doesn't turn out, it doesn't turn out. Okay, that's okay. So essentially, that is regularization, which is an important concept. It penalizes these weights and makes sure that the weights don't explode. There are different stuff, so you don't need square as well. So another regularization can just be modulus, so the magnitude. So this is also another regularization. So just the magnitude and lambda. So there are things called lasso regression, and there are things called ridge regression. The difference is in this part. So this like one is the lambda beta square, another is lambda mod beta. So the regularization is an important concept that you can go and read. Otherwise, I think these are all the things I wanted to cover. I think I missed certain questions somewhere. Okay, yeah. I asked you a question about precision, recall, and accuracy. Okay, so basically you understood accuracy. So let me explain it in this way. Okay, this is the ground truth. So ground truth is 0, 0, 0, 0, 0. I'm randomly throwing numbers. So this is the ground truth. Now these are the predictions. So predictions are, let's say 1. Okay, let's say these are the ground truths and these are the predictions. Now, what is accuracy? Accuracy is nothing but how many you got correct. That's it. Nothing else other than that. How many did you get correct? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 8 out of okay, 8 out of 14. So roughly the accuracy is 8 out of 14. So that is 4 out of 7, which is 56% or something roughly. So around 50 to 60%. So basically, this is accuracy. Now, what is precision? Precision is basically out of all your predictions, how many are actually correct? That's like, I mean, so okay, let's actually get to the official definitions. I didn't talk about metrics yet because there's a separate thing I have to cover, but otherwise, since we have time today, let's actually go over this. So if you remember the classification matrix, the classification report, this is another way to get the to measure the to measure the performance of classification models. It's called confusion matrix. So a confusion matrix is nothing but a graph having these sorry, it's not a graph. It's a matrix that shows you the true positives and true negatives, false positives and false negatives. So let me explain what those things are. So true positive means, let's assume like your class 1 is, let's assume that your class 1 is positive and class 0 is negative. So true positive means if the ground truth is 1 and your prediction is 1, that's true positive. True negative means if the ground truth is 0 and your prediction is also 0, that's true negative. Now false positive means, if you remember the fraud example, the fraud detection stuff that I explained during logistic regression, false positive means you predicted it as 1, but the actual ground truth is 0. You falsely told that it's positive. That is false positive. So it's defined here. So false positive is we predicted yes, but they don't actually have the disease. Okay, these guys are talking about disease, but essentially false positive means you said yes, but the actual answer is no. False negative is the reverse. You are falsely saying it is negative. You are falsely saying, you are actually saying no. You are saying no, but actually it is yes. So you are falsely saying it is negative. Confusion matrix gives you these things in a concise in a table format. So actual yes, predicted no. So in this table, where is the true positive? So this is the true positive, right? Actual yes and predicted yes. This is the true negative. Actual no and predicted no. Now, which is the false positive, up or down? Can anyone tell me? Is this the false positive or this the false positive? Okay. Yeah, 10 is the false positive because I said yes, the actual answer is no. So that's why this is called a false positive and this is a false negative. So now this matrix also is a judgment of the performance of my model. Now, where does precision, recall, and accuracy come into the picture? So this is where it comes in. So this is true positive, false positive, true negative, and then false negative. Now, precision means, let's look at the definition. When it predicts yes, how often is it correct? This means out of all your predictions, forget the ground truth. First of all, count how many predictions you made totally. It doesn't matter if you made it right or wrong, just count how many predictions you made. So predicted yes, count the whole thing. So you made 110 predictions. It doesn't matter if 10 of them are wrong. It's just that you made 100 predictions. Out of these 110, how many are actually right? That's precision. So that's why he divided 100 by 110. So this means you made 110 predictions. It doesn't matter if you're right or wrong. Out of that, 100 are correct. That's precision. Recall means how many actual true values are there? how many ground truth values are actually positive. So that is recall. So yeah, this is recall. So he took 105 because how many are actually yes. So 105 are actually yes. Actually yes means how many are actually ones. There are 105 ones. Out of that, you only made 100 correct predictions. So that's why he divided 100 by 105. This is recall. F1 score is nothing but it's the harmonic mean of precision and recall. It's just the harmonic mean. And then what else is there? Accuracy. I already defined it to you. So accuracy is this diagonal. So like it's just the whole thing. Like all the correct answers divided by the whole thing. It's just a diagonal. So it's like an arrow mark. This is precision. This is recall. This is accuracy. That's why confusion matrix is useful. I will put this link. It's very useful to understand this. Okay. So now let's get back to the predictions. So now you can see that if it says predict precision for this class, that means out of all my predictions, 60% I have predicted 0 as correct. Recall 100% means I have hit every 0 correctly, because all my model is doing is predicting zeros. It's not doing anything else. It's just predicting zeros. Obviously, if all I'm doing is predicting zeros, I have hit every 0. So obviously, whatever 0 I hit is correct. So that's why I'm getting recall like this. So that's why that's the simplest model, right? Let's actually do this. Let's actually, I'll show you one prediction. So why don't we so let me, where is it? Okay, instead of social predictions, all I'm going to do is I'm going to make 10%, right? Okay, 40 ones. So you see, I got recall of 1 as 1. Why? Because all I did was I predicted 0. Sorry, I predicted 1 and nothing else. So if I say 20 ones and then 20 zeros, I'm get 50-50. Why did I get 50-50? Because I made 0. I exactly made 20 ones and 20 zeros. That's why I got 50-50 over here. That's how these metrics work. So that is essentially these matrices. So basically, this is very key to understand. It's very important to understand this this concept here. So this is not just for machine learning. Someone mentioned biostatistical analysis. So Patrick, yes. So basically, in the field of medicine and like other fields also, type 1 error, type 2 error, these are actually very common in the medical data analysis. So did they get diabetes or not? Did they get cancer or not? These are actually very common metrics used everywhere. So it's just that they're also applicable in these problems as well. So yeah, I think that's it for today's lesson. If you have any questions, we have 15 more minutes. I'll be there till 6. You can ask me anything.
I'm just wondering if we would like to read more about this. Is there like a book that you recommend or something?
Okay. Yeah. So basically, in the slides that I've shared, I've actually put one link over here. Okay. This. So this is a very good book. I would suggest. It's called Pattern Recognition by Christopher Bishop. So this is a standard book that that many people follow. So Pattern Recognition by Christopher Bishop is such a great book that it has it's really the go-to book that I always I prepared my slides based on this book. So it's a very good book, and it's available for free. All you need to say, you just need to go into Google and type pattern recognition. It's already going to come. I mean, I didn't even say pattern recognition. Okay, Christopher Bishop PDF. You're going to get that PDF right here. So, it's a very, maybe it's not available, but it's a very good book. You can learn about this. So this book is slightly mathematical. You can learn that there, or else so you can go here. So you can basically go here like this. Waterloo's machine learning course is good, or you can I'll post a list of textbooks that are very good that you can actually refer to if you want to read short blogs. This is one. Is it okay? This machine learning mastery is something that I felt is good. This guy he writes blogs about these things. So if you don't want to get too much into math, but you just need math on a high level, and then you just want to start coding it, this is a good website. Machine learning mastery, he has everything. Like he explains everything very nicely, and then he gives you the appropriate equations, and then also he teaches you all these things, and then he also has code examples. So like I said, gradient descent, ordinary least squares, these are the different methods. So machine learning mastery is a good website. Yeah, apart from pattern recognition, there are some other books as well. So maybe, okay, let me show you this one. So there are certain books that I've collected. I've actually collected a lot of books. Okay, let me share my screen now. Okay, these are the books that I've collected. So these are some good books. Basically, okay, machine learning. What is this? Okay, this is also a good book, Machine Learning, A Probabilistic Perspective by Kevin P. Murphy. This is highly mathematical. If someone really likes math and wants to get into the deep mathematical concepts of machine learning, this is a good book for you. Kevin Murphy is a very good book. Otherwise, if you want to stick to top level concepts and move on, I would say pattern recognition is a good one. This Christopher Bishop pattern recognition. And then Andrew Ng's book is also good. This one is slightly different. It's called Machine Learning Yearning. He describes all the practical concepts of machine learning, like how to do train test split, what do you do, how do you actually decide when to drop the null values, and so and so. And then this is from Machine Learning Mastery. He himself wrote a big book on all the different machine learning algorithms. So other than this, there are these O'Reilly books. They are also nice. I've just read few of them, but otherwise these O'Reilly books are also good enough. So yeah, I can send you the links to these books anyway.
Thank you.
Yeah, someone asked a question about scikit-learn, TensorFlow, and PyTorch. So TensorFlow and PyTorch is actually mainly meant for designing neural networks and actually creating neural networks, like actually making your Okay. For some reason I got disconnected. Yeah, so we have 10 more minutes if anyone has any questions. Otherwise, that's it for today's class. So regarding the assignment, as I said, we'll have one final PDF where I'll submit. I'll send you all the questions, which will have everything. The weekly assignment is nothing but I'll give you homework to actually do what you learned today, so that next week I'll discuss the solutions, and then all these weekly homeworks, if you do them, they actually count towards your contribution or some your participation rate, and then also they will actually help you in doing the final assignment, which will that final assignment is the one that will actually be graded. So these homeworks, I'll just ask you to implement these algorithms again and then so and so. So that's why. Last question, which one? So Ivan asked me some. So Ivan, what did you mean? Which one? Oh, TensorFlow and PyTorch. So TensorFlow and PyTorch is meant for designing neural networks from scratch. sklearn has a different purpose. That's why. So you might not be able to compare those two things. Assignment 2 will be given tomorrow, and then you will have time until next Sunday to submit it. Assignment 1, try to submit it by tonight, or at least by tomorrow. You already seen the solution. I can go over your notebooks and maybe give you some feedback. Otherwise, yeah, it's just meant for, it's actually treat it more as a practice. You will actually learn to use these algorithms from scratch, and how to actually use the sklearn packages, how to do pandas data frame slicing. So when we get to feature engineering, there'll actually be a lot more calculations involved from next week. So that's why it's best to get used to pandas. So this week's assignment will have more questions on pandas and machine learning stuff as well. So because you would have to do lots of group by, apply lambda functions, so many things to run more algorithms. Yeah, final assignment is just one factor, but participation is also another factor. I think that's up to the organizers. Rohan and Zoe can answer that question if the final assignment dictates the phase 2 part. So okay, so actually, since we have since we just have 5 more minutes left, I'll just try to quickly show you this dictionary thing. So this is what I would do. Essentially, where is that? So okay, we already applied that lambda function. How do I get this into a dictionary? All you would need to say is, I think you would need to say something like this. If you say dict, okay, you won't get that. Sorry. Basically, you can say list. Okay, if you say list, you will get something like this. Now, right. If you say list, this whole thing is a list now. Let's actually, so you see these brackets over here, these brackets, you need to get the value inside. Maybe, so you would have to get 0. So I fetched the value inside. So I got all the titles. Now to actually convert this into a dictionary and count them at once, this is what you can do. So there is a library called collections. So from collections import. So you can do this. So if you say counter, now what happens is all I need to say is counter, and then the whole thing is counted automatically. I don't need for loop or anything. So you can just get this, get the value inside by saying 0, and then just say counter, and then you'll get the whole thing. Yeah, you can do toDict also. That's also another value counts and toDict also is correct. Yes. You can remove it. So the way to remove, I mean, you can have the, it doesn't matter if you have the dot or not, but if you want to remove it, then I would say, okay, I would say you have to put this round brackets. I think so. Yeah. Okay. If you just put these round brackets, the dot goes away. That's all. Okay, I think let's give back 3 minutes to everyone. I don't want to keep anyone over here. Anyway, I'm just staying until it's 6 o'clock, but otherwise you can feel free to drop anytime you want. Thank you for attending today's session and see you next week.